So two guest speakers this week, and they're both recorded, so they're not in person. But you need to watch them because then there's questions in the submission area on the guest speakers. So go ahead. Nope, we didn't. But so Tuesday, today, 21, right? Guest speaker is Fred. And you just click on it, it's a recording. You get the advertising first. Right, and it's done by Andy Dryden. This is during COVID. So this is Fred. So you get to watch that, and then there's some questions. And then on Thursday, there's another one, Jamie Kilgore. So same thing, click on it, find your 40 minutes to watch it, and then post up your answers to the questions about those guest speakers. Good? Questions on that? Ben, you got it? He's got it. I'm sure he's got it. Don't miss it. These are guest speaker field trip points, so you want those for sure. All right, Thursday, we know what's going on. We got prototype and structural analysis document due. We're going to talk about the structural analysis document some more, so I can answer more questions because I know we kind of rushed it right at the end. So what I'm looking for in that document is definitely some calculations. So, and some explanation of your calculations. So let's go back through that kind of slowly. And you can ask questions. So the basic formula I'm hoping to see is the bending stress formula. Okay, that's S sub B as I wrote it here. And that's moment. That's, what was moment again? What's the normal word for this? Rotation, torque, exactly. Yep. So we call it a moment in engineering, but like auto mechanics would call it torque, right? Other folks call it rotation. So I'll go over how to get that again from two basic setups. And you just want to simplify your system. So if your system is way cooler than either one of these basic setups, you just want to simplify it for the calculation. Okay. Don't try to overcomplicate this. The first situation would be like you have some structural thing that you're hoping to land on the table, right? So if you're going to land it on the table, then the table's going to support your system and you're going to support your system or the first table, right? So this would be what we call a simple beam that is supported in both sides. And the worst case scenario for bending would be the load in the middle, right? So that's the scenario we typically do the analysis on, is the worst case scenario. Yeah.
We just draw a straight line, right? Redesign, or do we actually have to draw the design of our...
No, you can just use, this can be your design, like just a basic beam for your design is fine. Just a straight line is fine too. I always give mine a little bit of depth because I think it looks good, but yeah, straight line would be fine. Yep. So this is called the free body diagram. So I definitely want to see that, some kind of graphic of your system, and explanation is great. What's it made out of? What's the cross section look like? We're going to need all that kind of stuff. If your cross section is complicated, simplify it. Just give me a simplified version of whatever you hope to make. Okay. If it's a box section, you're going to make a box, and it's hollow. You can do that. That's not that complicated to figure out as far as C and I. So C and I are the properties of the cross section. Everyone get what a cross section is? We kind of went over that last time, right? It's like slicing your beam in half. So the cross section of a 2x4 would look like this, right? A rectangle. And that would be in the strong position, because we learned last time that things that are vertically tall have good strength and resistance to bending. Okay, so the cross section is what your beam kind of looks like. If you're going to use a box section that is hollow, then your cross section looks like that. This is not that difficult of an inertia to calculate. These two things, C and I, strictly deal with the cross-sectional area. That's where you get both of those. I is inertia. And that is just a formula. And you can look that up for a lot of different shapes. If you want to snap a picture of my statics and strength of materials book, it has different shapes in the front cover. It has different shapes in the back cover. So for example, if you're going to use a box section, that's right here. So it does give you a couple different formulas, but that's just one for the X and one for the Y, because inertia is very specific to an axis. I don't need to get any deeper than that.
So when we're calculating inertia, we're calculating the whole shape of the structure.
Cross-sectional area. A 2x4 cross section is a rectangle. Yeah, slice it in half. The cross section of this table, if I cut through it, would be like a long rectangle. Right? It's that if you take a knife and cut through it, like the cross section of this thing would be a little rectangle. That makes sense? Yeah, so whatever you're going to build like, what are you building, Ben, out of that? What kind of shape? A triangle. So his cross section is going to be a triangle beam.
Okay.
Right? Okay. And those, those shapes, like a triangle is not in here because that's not a common building shape that we work with, right? But Google it and you'll get the inertia of a triangle. You can calculate it, no problem. But like the rectangle is just, BD cubed minus B1 D1 cubed. And then you just look here to see what D1 is. That might be DI, inside dimension, outside dimension, inside base, outside base, right? It's not complicated. Put it in the equation and you come up with your inertia. That's the number that goes here. Right? And this is inches to the fourth. A very unique unit. If you just had a rectangle, like no inner shape, then the inertia is base height cubed over 12. And I know that one because it's so common. We use a lot of rectangles, right? Anytime we build with wood, that's a rectangular shape. Questions on inertia?
We have to solve one formula for it, right?
You have to solve the formula for what? Yeah, well, you have to calculate inertia to put it in here, correct? And our goal is to get a bending stress, right? So you need inertia. Yes, you got to calculate it. Yeah.
So when you said a cross section,
Cross section.
does it matter like if it's like, for example, a rectangle, we have it the long way or
Like the strong position or the weak position?
would that be
Yes.
based on how the structure built that which one we calculate?
Yeah, how you build it. Yep. So however you plan to build it, then calculate that inertia. And it definitely matters because what we're cubing is the height, right? The height is what gets cubed. So here the height is bigger, so inertia goes up. Here the height is smaller, so inertia goes down. Irina. Yep. Yep. And you can snap a picture of this if you're doing a tube, a hollow, or a pipe, right? That's different than a solid, for sure. Yep.
So for the distance for the force, do we have to create our own like physical weight?
For solving this, yeah, so let's talk about that. Because this diagram, the picture of the beam itself, right? This is 8 feet from here to here. So this is 4 feet, right? This, you got to put some forces in to calculate the moment because we need the moment too. So you need the moment, the C value, and the I value to calculate the stress. You do it on your system. So how much weight are you transferring across your system? How much does the baseball weigh? Anyone weigh it yet? Baseball? Yeah, I don't know. I think it's like a bush here. Maybe it's heavier. I don't know. Well, we know how much this is, right? This is a quarter pound. 0.25 pound. So when we transfer this across, it ends up in the middle at some point, right? However we get it there. If this is our system, right? I'm just trying to give you examples. Maybe this is your system where, you know, this is the cantilever fishing pole thing, right? Where it has no support, no arrow going up on this one. We'll do that one next. So this one, the 4 ounces comes across, 0.25 pounds ends up here at some point, right? That's the worst case scenario for bending. The load in the middle, the truck in the middle of the bridge, right? Does that make sense? Okay, so we take kind of that snapshot of that worst case scenario. And then our structure weighs something. How much does your structure weigh? His weighs 2.5 pounds. So I've also said the weight of something you put through the geometric center. So that means we've got another 2.25, 2.55. Or whatever your structure weighs, right? That's just what his structure weighs. But that goes through the geometric center, giving me a total load at the center of what? 2.55 plus 2.5, right? Yeah. Everyone okay with that? All right. Yep.
What about the weights of the edges?
Like here? Yeah. So that's where we had the little conversation about equilibrium. Like if I'm just standing here and you don't see me sinking into the ground, then my 170 pounds is being resisted by the ground. The ground is doing what? Yeah. Up 170, down 170. Equilibrium, right? So if I have, how much did you say this was? 2.8? 2.55 plus 0.25. 2.8 total pounds coming down. How much do I need going up? 2.8, but it's symmetrical, right? So how much goes here and how much goes here? How much goes here and how much goes here? Half of it, exactly. So what's over here? 1.4, 1.4. How much total coming down? And how much total going up? 2.8, right? Equilibrium. Sum the forces in a direction. Every force has an equal and opposite reaction. That was Newton who figured that stuff out. That's what equilibrium is, and that's, of course, what we want. All right, so now we have these loads. Now we need to know what the moment is, like the rotational effect. So the smallest, littlest fibers in your system are feeling this load and resisting it. We hope, right? That's what we hope. So we're trying to forecast that, like figure out, hey, is this really going to resist it or not? And those little fibers are trying to like bend, right? So the bending happens here, correct? And the maximum bending, the worst spot is where? In the middle. That's where it's feeling like the most bending stress. So that's where we do our analysis right here. I want to know what the rotational effect is right there. Okay, that's the moment. And I said, hey, moment is equal to force times distance. Simple equation, force times distance. But this is where I want the moment. So I look for a force furthest away from that point, and it's this, 1.4. I could go this way, but it's also 1.4, right? So since we have symmetry, that makes it a little easier. I have 1.4 pounds. How far away from that point? 4 feet. So I have 1.4 pounds for feet. Force times distance. Good? Everyone see why I chose the middle? Because that's where the worst bending is, right? Yeah, so what's that number? Anyone got a calculator? A room full of engineers and no calculators, really? Come on. I wasn't kidding, I was serious. 5.6. What's the units? Careful. Foot pounds. Pounds times, right? Yeah, not per. Right? Foot pounds. Foot times pounds. That's torque. That's our moment. That's our maximum moment. Good? All right, so now we're ready to calculate this stress. Does anyone remember what C was? I did it really quick. Good. It's, what is C? He's close. Something about the middle. It's true. It's the distance. So it's cross section, right? Whatever your cross section is, it's the distance from the geometric center of your cross section to the outermost fiber. So let's just say we have a 2x4. Let's say that's what we're working with. That's what this beam is a 2x4. So anyone know what the size of a 2x4? It's not really 2x4. It's not, that would be too easy. It's 3.5 by 1.5. That's what a 2x4 is. A 2x10, anyone know what a 2x10 is? 1.5 by 9.5. Yeah. Why do we do these things to ourselves? It's so we know what's going on and the rest of the public doesn't. That's what. All right. So C is the distance. It's from the geometric center. It's also called the neutral axis, but it's from the geometric center to the outermost fiber. Yeah. So it's half of the height. Yeah, because when it bends, it acts on the long axis. So we measure it from this x-axis to the outermost fiber. So that is C. If we had an L shape, a little more tricky because you have to know where the geometric center is, right? And it's in a unique spot with an L shape. We have to be able to calculate that. But then there's the C value, and here's another C value because that one's not symmetrical, right? And it's the greatest C value you can find in your cross section. So most cross sections are symmetrical, like a rectangle, and it's pretty easy, just half a 3.5. Okay. All right. So we'll use this. We'll use our 2x4. It's kind of big, right? Or we could use Ben's shape. How big is your triangle? Approximately. What is that, 1.5 inches? So if we had a triangle like this, right? Maybe it's equilateral, 1.5, 1.5, 1.5. From there to there, you know, I could find that formula and look it up, but it's probably going to be like 1 inch, right? From the geometric center to the outermost fiber. So the C value is here. This is the side 1.5 all the way around. Again, you can look it up and calculate it. So you just need that from the center to the outermost fiber. All right, so let's run our bending stress. My moment is, what was my moment? 5.6 foot-pounds. And we're gonna just put in 1 inch as a C value, like maybe Ben's triangle. It would be a little bigger with a 2x4. But it's just a length, right, that you come up with from your cross section. And then we need an inertia value. So again, if I was going to use the triangle, I'd have to look it up. The L shape, I'd have to look that formula up. If I use a rectangle, that's the formula. Right? So whatever your shape is, you can calculate. So I'll use a small rectangle. Let's say our rectangle is, I don't know, 2 inches by 1 inch. Right? Maybe that's a reasonable cross section for this project. And we'll just say it's solid. We'll keep it simple. So 2 inches high, 1 inch wide. My formula for inertia is going to be 1, 2 cubed over 12. Right? Height is 2, base is 1 over 12. And don't forget to cube it. Somebody run that for me. Because you all got calculators. Because you're all prepared. Ruben's like, wish I had a calculator. 2/3? Can you give me the decimal point? What, 66? Yeah, repeat. And what are the units? Inches. To the 4th. So 0.666 inches to the 4th. So here's my bending stress equation. And what I want out of bending stress is I want PSI, pounds per square inch. That's the unit I need. Okay. So what kind of unit do I have going here? Foot-pounds times inches divided by inches to the 4th. We have a unit problem. So we have feet times inches. That's not going to work. I need the feet in inches, right? Because then I have inch times inch, and down below I have inches to the 4th. So that would give me inches squared down below, pounds above PSI. So I need to convert this foot to inches. How do I do that? Anyone know? It's called unit analysis. I'm sure you've done it. You put in the conversion, right? Because if we're going to get rid of this foot right there, I have to divide by feet to get rid of it, correct? So that means I put, 1 foot down below, and then how many inches are in a foot? 12 inches above. So then the feet cross out, and I have inches, inches, inches to the 4th. That all works, right? So it's a multiplier of 12. So 5.6 times 1 times 12, divide by 0.666, divide by 1. Gives me pounds per square inch. Yeah? Somebody run that number for me. Everybody got it? 8.4. Anybody else get 8.4?
That's like PSI, right?
That should be pounds per square inch once the units cancel out. Yep. I get 100.9. Anybody else? Yeah, yeah. So we have a bending stress, S sub B of 100.9 PSI. Everyone okay with how I calculated it? Not too lost in there. Is that good or bad? It's a trick question. Depends. That's always a good answer, isn't it? Depends on what? What the material is, what it's made out of. If it's made out of silly putty, that's bad, I'm sure. I'm sure silly putty has no resistance to bending whatsoever, right? If it's made out of titanium, you can probably carry that, no problem. If it's made out of wood, the bending stress for wood is 900 PSI. So is this good or bad? Good, by magnitude of like 9, factor of safety of 9, right? Excellent, means you could make your beam smaller. You're way over designed if you're 9-to-1 factor of safety, right? That's what that means. This means something. We compare it to a material that we look up. You had your hand up. Yeah, I'm actually going to write it a little prettier too. Right, we had that times 1 inch. That was our C value. And then we had 0.666 inches to the 4th. And this foot had to go away because foot times inches and inches below, that's not, we want all those lengths the same, right? So then we put in the factor of 12 inches per foot. And I put it in that way because I want the feet to cross, right? So this is just what we call a conversion, right? 12 inches per foot. So you can put it in there. You just want the feet down below. So does that help? Yeah. Okay, perfect. And then we got this. Perfect. Excellent.
So the stress bending is not rely on the material, it's just
yeah, so all of this calculation had nothing to do with material. It had everything to do with force. That's your moment. Your rotation is your force, right? And then it just had to do with these properties of the cross section. So when we calculate bending stress, I don't even think about what the material is made out of. It doesn't matter because it's all about that cross-sectional shape, right? It's all about the rectangle or the I shape or the W shape or whatever we're working with. Then when I get my bending stress, I go, oh, if I want to use cardboard, what's the allowable bending stress of cardboard? Will it take 100.9 PSI? If it will not take that, then I need to size up my beam. The beam needs to get bigger because as the beam gets bigger, the stress comes down. As the beam gets smaller, stress goes up. You have to look up the material. Yeah. Yeah. Whatever you're building out of, you want to look it up. And again, like if you're building out of cardboard, that's a very hard material to get material properties for because it's not a common building material, right? You can get plastics, all that kind of stuff, PVC, you can get all of those kind of bending stresses, no problem. So that's it. And honestly, I don't care if you come up with like, hey, this could fail. That's fine. That's a forecast of what could happen, right? Or our beam's way over designed. That's great. That's all I want. Good?
What additional information? Just the stress bending and maybe some information about our design.
Yeah, information about your design and then what you think of the number you calculated. Yeah, that's it. Is that helpful? Okay, good. You'll get like you'll get a whole class in this part. It's called statics, and that's just understanding forces and all the different scenarios. And then you get a whole class in this, and that's stresses, where we do bending stress, tensile stress, shear stress, torsional stress, deflection, all of that, right? So you get good solid 12 weeks of this, and you get a good solid 10 weeks of this. So you getting it all in one day is a little rough. I get that, but you can handle it. That moment is rotate. The moment is rotation. That's torque. Yeah. What we don't think about is all the other stresses. You're just doing one stress, bending stress, right? There's shear stress. There's torsional stress. There is buckling, all kinds of different failures that can happen. We're just doing one little piece for fun, because that's what we do for fun. Like, you know, nurses stop the bleeding. We calculate stresses. All right. There was something else I wanted to do. Where's my list? Yeah. Have you all had Excel? Has anyone had Excel? Who's had Excel? Who loves Excel? Oh, hands went down right away. Yikes. Come on. Excel's like our favorite tool. There is. It's one credit class, but it's nowhere near as fun as this class. Yeah, they just do lame stuff in there. They don't do formulas and stuff. So yeah, you have an Excel lab, and you have until like the 26th to get it done. So I'm going to do a little Excel now, and then I'll do Excel on Thursday, because prototypes don't take that long, and we can use that lab to do the Excel lab if you've never done Excel before. And then I'll be readily available to help you with Excel. But I want to just do a little bit now to get you bump started, and then show you the lab. This is the lab right here. I did load it up. Essentially, you're going to put 3 shapes in Excel. This is an example. You can use any shapes you want. I did say I would like easy, hard, and difficult. So not all just super lame shapes. Challenge yourself, right? And then you're going to calculate area, you're going to calculate perimeter, and you're going to calculate volume at a depth of 20 inches. Okay? In Excel. So Excel, you can put alpha in Excel. That's letters, right? You can write a letter in Excel. I don't recommend it. It's not great for letter writing, right? But you can then also build formulas and calculate things like your calculator. And then you can also build formulas and display the formulas. So that is for us. When you take the Excel class, you learn to run formulas, but they never show the formula. And that doesn't work for us. We have to show the formula and then run the formula, right? If I'm going to calculate area of a rectangle, does anyone know what the area of a rectangle is? Base times height, super simple, right? But in an engineering document, you have to show that formula. Area equals base times height. Then you got to run the formula, okay? Because when we look at each other's work, I got to know what formula you're running and then how you're running it, kind of thing. So if you've never run Excel before, I like to run in page layout. This is normal view. When you come into Excel, it looks like this. It's okay. I'll zoom back a little. You can see the page break here, that dotted line. I prefer the page layout because then it looks like what the paper is going to look like. And you know right away if you're bleeding off the paper, right? It's a bunch of cells, right? And you can type in these cells. So I can do alphanumerics and it'll just type like crazy. Okay. Yeah, I know. I'm an excellent typer. All of this information is in that cell and it shows up here when I click on that cell. Okay. Now it'll bleed onto the cells next to it if there's nothing in that cell. Does that make sense? So if I put in here like 42, boom, no more does that text show. It's still there. See, it's all here in this cell. It just doesn't show because there's something in the adjacent cell. So if you want to write a sentence or a paragraph, just clear the cells out next to it and everything's good. Right? It'll show back up. So alpha in one cell. Keep your alpha in their own cells. Keep your numbers separate from the alpha. Okay? It sees this as 42. If I write 42 inches, Now it does not see it as 42. It sees it as some alpha number thing that it can't do anything with. So you can only use numbers if they're in their own cell and they are a number. Does that make sense? So if you want to put 42 inches, and I'm a big fan of units, we should have units on our numbers, right? I would put in 42 and then do what? Yeah, inches in the next cell, right? So all of these little grid lines, they don't print when you go to print. You see them, but when you print and hand it to somebody else, it just looks like a fancy Word document, right? And then they don't even know it's being calculated. So Excel can calculate. That's the cool thing. All right. I'm going to put in a shape. So under insert, there are shapes. And these do not go in cells. Oh, I didn't want that. Let's do rectangle. These are just like laid on top of the page. So not in a cell, just for me to look at, right? And then I'll size it. I'll say, oh, it's 12 inches here. So this is what I'm looking for, and we'll say it's 6 tall. And sometimes you got to get creative, like where your units are, right?
How do you make color?
How to make what? This? How to make it reappear? I'm confused. What? I don't.
He's talking about how do you move the text either justified to the left or right.
Oh, when I just moved the inches thing? Oh, wow. You're paying attention today, Ben. That's awesome. So yeah, it's just like Word, right? You have all the little justifications. So right here is how I did it. So if I wanted it left. So when you type in alpha, I don't know why my caps is on. That's bugging me. It's left justified. And you type in a number, that's right justified. That's just the default, right? I could just like highlight both of those and say center them. So you have controls over where you put things in the cell, and you have controls over cell size. So I can go up to here, this column, and I can shrink it and raise it. Be careful with that because it changes the whole spreadsheet. Everything down below gets mucked up. You can, yeah, you got so many things you can do, fancy stuff. You want fancy stuff, you talk to those two right there. They know Excel. All right, let me keep going because here we're getting to the point of like the whole lab is to set these kind of shapes up, give them size. I have given them size, right? And I think I said, I didn't print it. Oh, I did print it. I want you to actually do some shading. So input cells are going to be shaded green. So input is where you input numbers, right? So I input the 6 inches. So I'm going to shade that green because that's what Professor Troy said to do. So those are 2 inputs, right? Everyone understand that? An output would be area. Like I'm going to calculate the area. So I'll get rid of me and I'll put area. And I'm going to say area, this is alpha anyway, right? So when you want to edit, this is a good point. You click on the cell and then you got to go click up here to edit because this is where they call it the formula bar, but it's also the editing location. So if you click up here, then you can type in anything. Oh yeah, very good. I'm going way back probably like this is I'm probably teaching you Excel 1 and there's all kinds of fancy ways to do shit. Yeah. Get used to that. What is it? Length, what'd you say it was? Length times height? Something like that, right? So I want to see the formula first, right? And then maybe below that you could put area and I would stick the equals in. Oh, I didn't want the whole thing. Oh, look at this, Ruben, watch. Check that out. I'm a quick learner, don't you think? Yes, you are. And then I'm going to put the formula in its own cell. Right? Always got to have it separate from everyone else. Anyone know what you start formula with? Pros. Equal sign, yeah, man. So if you type in the equal sign, Excel knows right away, oh, we're gonna make a formula, right? So what we want to do is we don't want to multiply 6 times 12. We want to multiply cell times cell. We want the cell location and the cell location. And all you have to do is click on it and it'll put the cell location in for you. And then you can just think about like, oh, multiply, what would that be on my calculator? Or what would the symbol be for multiply? Star, something, right? That works. Try it. If it doesn't work, then you'll have to maybe research a little bit, but most of the things work very intuitively. And then the next cell, and then I hit enter. Then you should get your dang calculator out and check it, because you could be mucking something up and just, oh, I think that's right, right? But that looks good, right? That's what I want. This is an output. I think I said shade that, not green, red. That's really bright. I don't like that red. I want a softer, more gentle red. Where's the rest of my reds? More colors. Oh, yeah, we can get lost in here forever. That's not really red.
Do a custom color.
Oh, all right. Yeah, this is going sideways. Oh, that's pretty red. Okay, now I want no fill. All right. Yeah. And then you should always check it, and checking it would be just changing an input. And it should automatically like, oh, pump it out. That is the power of Excel right there. Not setting it up, not the, 25 minutes to set it up, or the 10 hours or 10 days if you had a big one. It's once you get it set up, then you can use it and just pump in numbers and get new numbers out, right? So you're going to do this for 3 shapes and then more parameters like area, perimeter, and volume. Cool? Yeah, and then of course we should have some kind of unit here. There is a pi. Yeah, there's all kinds of equation symbols and stuff that, yeah. So if you want to display a formula that's trickier than this is pretty straightforward. I just used alpha. Then you want to insert an equation. If you pull that down, it's going to give you a bunch of example equations. Okay. And what you do is just click on it and then I'll plop it in here and then you can modify it. Right. And really what I want is I just want inches squared right now. So I could actually modify this and say, where'd it go? Boo. Oh, maybe I can undo it. Come back. Come back again. Oh. There it is. It's gonna, oh, I see it's highlighting it. Bang, bang. That's not cool. No, I don't want to. Yeah. Super cool. It's going to look pro. Like, I don't know about this text up here is looking pro, but if I go print, right? That's what it's going to look like. Yeah. That's what we want. A little softer colors, please. All right. Good. Good start on Excel. Yeah. And then if you need help on Thursday, that's what lab's for. So let's do the 26th, though. You have a lot of time. So I would put that off until the night of the 25th, Ben. Yeah. Do it then. Exactly. I just like picking on you. All right.